Hello everyone, welcome to our final 2110 design project presentation. I'm Dylan Mason.
And I'm Canute Brody.
And we will be representing Group 4. Now it's time to introduce the problem we are all too familiar with at this point. The problem was to use a structured design process to design, build, and test an automated robotic system that accomplishes a series of basketball-themed physical tasks, which are pass, jump shot, and dunk. Down below you can see some of our very initial design sketches to solve the problem, as well as the competition arena, where we would later prototype and test our robot. The House of Quality was the first design tool we used, which helped us prioritize what aspects and functions of the robot were most important. The notable customer requirements, in red, were things like stable and straight drive, and of course non-hazardous, and notable engineering requirements, in green, are activates when pressed and of course scores points consistently. The spec sheet was another design tool we used to help prioritize important aspects and functions of the robot. Several were necessary requirements for our robot to remain eligible to compete, such as remaining under the $100 budget, as well as staying within the size constraints, and others refer directly to the expected robot performance of each of the physical tasks. Two other useful design tools we used were the morphological chart, with lines showing each of our alternative design solutions, and the evaluation matrix. Both of these tools allowed us to brainstorm and analyze actual mechanisms for each subsystem of the robot, and how well certain mechanisms would work together. Several of the design decisions shown to be effective by these tools were successful for the duration of our robot testing, such as the wedge and the single axle drive. After lots of team discussion and comparing the effectiveness of certain mechanisms in different combinations with one another, our final design decisions for the robot were made and can be seen in this morph chart on the right. Initially, our final design selections for each subsystem were pneumatic pusher for the pass task, PVC slingshot for the jump shot, front-mounted wedge for the item collection, PVC ramp for the dunk, no sensors or rotation as the wedge eliminated their need, single axle drive to move forward and backward, and derive all other power electrically. The only major shift that was made on this morph chart was the switch from PVC slingshot to a retrofitted PVC pneumatic push cannon. This switch was made after Sprint 1. Speaking of Sprint 1, for this competition, we expected to score full points for a successful launch, pass, and jump shot on all three trials. The launch and pneumatic pusher for the pass task worked successfully on all three trials, but not the slingshot for the jump shot. The jump shot hit the rim on one of our trials and missed long on the other two. The problem with this design was that the four rubber bands had so much power, it was too difficult to consistently bring the cut back to the same position every single time, thus making the power very unreliable. Going forward to Sprint 2, we aimed to switch the jump shot to the pneumatic cannon, as well as get the drive, hopper, and tape measure ramp functioning. For Sprint 2, we were able to get all of those things accomplished: the drive, the hopper, the ramp, and the pneumatic cannon. After initial testing, we expected to receive full points for the launch, pass, jump shot, collection, and score the money balls for the dunk, as we had yet to figure out how to dunk the initial stock item. Our actual results for this competition were full points for the launch, pass, and jump shot, so our new cannon worked great, and we scored both money balls in the green on two different trials. But for our final trial, a PVC pipe fell into the ramp and caused it to unwind. To counteract this going forward, we added a little cardboard roof over the ramp to protect it from any pipes, as well as having the tape measure deploy later than we had initially. We also added a back and forth drive at the end to ensure the pipes were out of the way. Finally, we added a cup to the front of the tape measure to collect the first stock item for later dunking. These decisions led to our final competition robot, and now I'm going to pass it over to Canute, who is going to tell you about how the robot was fabricated and how it functions.
Thanks, Dylan. I'll be going over each of the components of this design, but first we'll start off with the code. So as all of you know, it begins with a button press, and we start to define the libraries and the variables in that time as well. Then we start a timer, and our first timer count is just a slight delay so we can get out of the way before the pneumatic pass and jump shot trigger. Then the robot begins to drive forward to knock over the pipes and get the money balls, as well as collect the lower stock items. We have another timer going until it reaches close enough to the dunk zone, and we found that time was accurate enough and encoders weren't needed. Then we initiate that small drive back and forth step and begin to have the tape measure unroll. And then we wait until that is completely unrolled. And again, time was accurate enough for that. Then we pull back in the solenoid, all the 3 balls run down, and our run is complete. So in terms of mechanisms, we'll start with the pneumatic pusher. It's a fairly simple mechanism, essentially just made up of a wooden sled, which is attached to the piston on the threaded rod that's included on the piston with 2 bolts. That's just manufactured out of standard wood, actually wood scraps. And then we also have the piston, of course, which is attached to the frame using custom 3D printed U-clamps. So the piston is mounted centrally, and we have a little bit of spacing so that the sled just barely glides above the ground, about 1 to 2 centimeters above the ground. And it starts off in, so of course it's not past the foul line. And then during operation, it extends out and pushes the ball towards the bucket. Here's a video of it in action. Moving on to the pneumatic cannon that accomplishes the jump shot task. Within that PVC pipe, the pneumatic piston is mounted with this 3D printed ring mount, which hugs the pneumatic piston and then also attaches to the outside of the inside of the PVC pipe. And then inside, there were also supports made of metal to sort of support those mounts. And then the whole thing attaches to the robot frame using a threaded rod on the top, and that allows for some adjustability as well. And then within the piston PVC pipe itself, there's a 3D printed cup, which sort of holds the ball in place until the piston pushes it out and fires the cup towards the bucket. Here's a video of it in action. So in terms of the drivetrain, we have 4 laser cut wheels, which are each made of multiple layers of MDF glued together, and then they're wrapped in tape to give a little more grip for the front drive wheels. We also have laser cut multi-layer gears that are attached to both the motor and the front drive axle. We have a 2-to-1 gear ratio, which gives us the speed we need to actually knock over the PVC pipes into the hopper. And as you can see with the placement, they're pretty central, but a little bit biased towards the front, just to give us room for some of the mechanisms that hang off the back. In terms of the wedge in the hopper, for the hopper, we used a mostly cardboard construction, which ended up working very well, and we were able to get our complex shapes very easily. As you can see within the hopper, we have some purple foam, which, as well as looking really nice, also helps cushion the balls when they land into the hopper and makes it so that they don't bounce out. The wedge on the bottom is laser cut out of thin balsa wood and then attached with some additional wood supports to the frame about 1 to 2 millimeters off the ground, just so it glides over. And that helps PVC pipes to be knocked into the hopper, and then the stock items fall into the hopper as well. And you can see that in action in this video. So one thing you might have noticed in the last video is a small cup that is attached to the tape measure, which sort of acts as an extension to the hopper itself. So that small cup picks up the lower stock item and holds it in front of the hopper, while the other 2 balls are held back with a solenoid, which you can see in this picture as well. In terms of the tape measure itself, we have a spool that was part of the original tape measure body, and then we have that mounted to a motor on some MDF sort of connection points. We have that glued to that, and then when the motor spins, the tape measure extends. One thing that really helps with that is that behind 36 inches, so essentially behind the maximum extension length we need, the tape measure is glued to itself. So that helps it stay compact and not start to unspool sideways or anything like that. So in operation, it collects all the items and then it begins to extend with the lower ball on the front. Then the solenoid releases and the other 2 balls roll down the tape measure, knocking all 3 into the cup. So now we'll sort of go over our final competition expectations and performance. So we had been able to demonstrate in the lab that the robot was capable of getting the maximum score. So getting the jump shot, the pass, the launch, of course, and then all three balls into the green cup. So that was our expectation. Unfortunately, that didn't go quite to plan. So during all three trials, essentially what happened was a money ball did not land into the hopper at least once. And then on the first trial, the balls went into the yellow cups instead of the green cup. I think all of these have something to do with the field in the competition arena being just slightly different than the fields in the Idea Lab, and it just sort of being on the fringe cases of it not quite working perfectly. But all in all of our mechanisms functioned as they should. We accomplished over the minimum threshold for a perfect score, and we're very proud of our performance. This here is a video that we had in testing of our robot completing a maximum score. So let's take a look at that. So as you can see, it gets the jump in the pass, it collects the lower ball, connects to upper balls. It goes back and forth to let the pipes get out of the way. Then, as you can see, the tape measure extends. Then the solenoid retracts, and all three balls go into the cup. So that's similar to what happened at the competition, except on the first run, it didn't quite extend far enough. And then on the other runs, the left ball just didn't quite fall into the hopper. But thank you so much for listening. This has been a really incredible class, and we'd love to answer any questions you have. That's all, folks.